Hi everyone. I know it's lunchtime and Indian STATPHYS has a fairly large community who likes fish, and I know it's probably appetizing. And hopefully, when you have your next fish meal, you would think about this talk on maybe fish do really something really interesting. So I'm going to argue that the schooling fish that you're seeing here can be called what is noise-induced schooling, and I'm going to describe what I mean by that. And before I go, I just want to thank a bunch of people who did this work. Jitesh Jhawar was the PhD student who did bulk of this work. And he is currently a postdoc at Max Planck. And these are collaborators, Richard, who was a postdoc at NCBS, Danny, who is in chemical engineering IISc. This is a Malayali fellow, Hari Krishnan, who set up the experiments. And surprisingly, the fish survived and we were able to do experiments despite being a Malayali. And Amit and Tim Rogers are the other two people. And I could not find a picture of Tim who was looking towards us. Okay. With that short note, let me quickly introduce what do I mean by noise-induced state. So this is an equation that is probably familiar to most of you. It's a very simple Langevin equation where the deterministic term is exponentially trying to take the m back to 0, whereas the noise is pushing it away in a typical thermodynamic sense. So the steady state distribution of the variable m would be a Gaussian around 0. Okay, this is the sort of classic Langevin equation we all study. However, in many non-equilibrium systems, the stochasticity can arise in many interesting ways, and one such way is called the multiplicative noise. So here the noise term is additive to the the state variable and the differential equation. However, the strength of noise can also depend on the state variable itself. For example, in this equation, while the deterministic term does exactly same as the standard Langevin equation, so in this case, the strength of noise depends on the state variable itself, and in fact, it is maximum when m is equal to 0, and it then sort of decays as m increases. So what this means is that as the deterministic term tries to pull the systems towards 0, the strength of noise is increasing. So there is a tension between deterministic term and the stochastic term, and we can mathematically show that if the sigma square is comparable or greater than alpha, I'm not getting the prefactors right here, you can actually get some very interesting results. So when sigma square is less than alpha, you again get the steady state distribution exactly same as this case. However, when you have sigma square which is more than a threshold value, you actually get a dramatically different state. The most likely states are actually not deterministic stable states anymore. However, they're actually fundamentally different from and those are called noise-induced states, sort of broadly defined. When the most likely states are qualitatively different from the deterministic stable states, we call them noise-induced states. Okay. So what does this, what we're basically claiming is that something like this is really happening in our fish school. And how do we do that? So we first calculate the standard Vishwesha order parameter. We will look at the orientation of each fish from the videos. These are, fish that are found in Kerala. They are called curry and when we put them in fish tank without any stimuli or whatsoever, they spontaneously school. And from the simple, image processing techniques, we can calculate the order parameter, which is the average of all the orientations of fish. Now, something important and interesting I want to highlight here is that unlike a typical statistical mechanics problem, the number of particles here are really tiny. I'm really looking at 30 fish or so, whereas much of the theory of active matter sort of looks at thermodynamic limit, right? So what we really need to do is to look at the mesoscopic dynamics that captures stochasticity arising from small number of interacting particles. So how do we go about doing this? I told you if you have an SDE, how can I conclude that there is a noise-induced state, right? So what we now do is, from the data of this, this time series, we basically construct a differential equation of this type, which also accounts for the noise. And how do we do this? We can compute the deterministic part of the equation by looking at the jump moments. The first jump moment it would actually get you the deterministic part, whereas the second jump moment would basically will be able to get you the stochastic part. Okay. And the basic idea is fairly simple. When you have a trajectory of a stochastic variable, the average displacement from a given value determines the deterministic term, whereas the variations in the around on that average determines the stochastic term. So with this, what we do is we basically apply this to time series data that we get from data, and we look at what is the SDE, what is the stochastic differential equation that describes the data. And remarkably, the equation turns out to be very, very simple, and this is the construction for the deterministic part. So what this shows is that, so of course the two equations I showed you in the beginning, they were scalar order parameters. We have a vector order parameter here, therefore there are two components, and both the components are basically planes. What this tells you is that the order parameter, Vishwesha order parameter, basically decays linear, shows an extremely simple deterministic term, which is the dm by dt is minus alpha m. Okay, which means that if you would think that if you wait long enough, m must be equal to 0, therefore the system is in disordered state. However, surprisingly, the noise term does something very, very interesting. In fact, almost exactly identical to what I was showing as an example of noise-induced state. So noise term is not a constant. It doesn't, it actually depends very strongly on the value of the order parameter, which means that what this really means is that when m is 0, which means when the fish school is disordered, the noise is maximum. When the fish school is highly aligned, the noise is really minimum. And another very interesting fact is that this stochastic term also depends on the number of fish that we use in the experiments. Okay, so putting these together, deterministic term is n independent. It doesn't depend on the number of fish we use in the experiments. The stable equilibrium that this, if I had ignored this part entirely, I would have said that the stable equilibrium for the system is disorder, right? However, if I look at the data, if I just plot the histogram of the observed states, it shows this is mx and my. These are basically the two components of the order parameter. What you see is the most likely state is basically a ring at mod m is equal to 1. Which means that the most likely the observed state is really a highly ordered state, whereas the deterministic prediction would have been that it's a disordered state. And the stochastic term depends on the system size, and it also depends on the current value of the order parameter itself. So all these put together, there are two very interesting things here. We are able to construct a stochastic differential equations from data. And secondly, and this equation in turn suggests that the observed noise is driven by this stochastic term in a really prominent way, in a non-trivial way as well. Okay. Again, just to recall the two examples I showed you, in fact, the remarkable thing is this term here looks almost exactly like this term, but in the vectorial representation of the order parameter. Okay. So now what does this mean in terms of fish behavior? What are really fish doing here? To understand this, we built a simple individual based model, which sort of was motivated by various models that exist in literature. So we assume that fish can do sort of three simple behaviors. The first one is a spontaneous turning. So theta I represents the current direction of a fish. It can become theta I plus an angle which is basically a random angle, which we model as a truncated Gaussian. The second one is that of copying interaction, when fish can also interact with another fish in the group at a rate c and then turn towards that fish. So we pictorially, basically, if these two fish interact, this guy will turn towards this guy at some rate c. Okay, and this is entirely a symmetric interaction. There is nothing asymmetric about this. We assume a third interaction, which is a higher order interaction called ternary copying interaction, where if there are three fish that interact, a fish who is in sort of a misaligned with the other two will turn towards one of those two guys. So basically we are looking at three interactions, sort of three types of rates in this model: a spontaneous or a random turning, pairwise copying, and a ternary copying. Okay, and then what we do is we derive. These are basically chemical reactions, right? Which happens at stochastic intervals. What we do is we sort of account for the fact that the number of individuals in a group can be finite, and use methods of expanding Fokker-Planck equation accounting for the finite sizes, and then we derive an SDE for the order parameter. Okay, order parameter is defined exactly same as the Vichek order parameter. What we find is that for this model, the rate of change of the order parameter depends on, has a cubic term as in the classic Vichek model as well, and a stochastic term which has a similar multiplicative noise structure as well as a group size dependence, a system size dependence. And now in this equation, if I set h equal to 0, I just want to remind you that h corresponded to this interaction, the rate of one fish turning towards two other fish. If I set h equal to 0 and a is equal to alpha and c is equal to beta, that's when precisely we get what we had in data. Okay. So what this suggests is something very, very simple, that fish seem to be doing these two interactions, but not this, because we in our, when our data derived SDEs, the higher order term is not present, right? We don't have the higher order term, the cubic term. Therefore, this interaction is not happening in the fish that we studied, but only these two are happening. And that simple pairwise copying interactions cause noise-induced schooling. And this is the equation of the alignment dynamics when you put together a bunch of fish. Okay. So with that summary, I would like to sort of end my talk.